All right, welcome back everyone. So let's start today's lecture. Before we do that, any questions about the last class or any other logistics and stuff? No? All right. We hope that it'll probably take a few more weeks for the class size to settle down. So I know you're still on the, people have to sit on the stairs. But again, assuming we can allow it for some more time. I don't know what the regulations are as such, but it's probably okay. As long as nobody comes and tells us otherwise, you're welcome to do so. All right, so we'll start talking about, as we did briefly last time, the Bayes optimal classifier. And then today we'll look at a particular classification technique called naive Bayes, which is one of the simplest classification techniques, but it still works pretty well in practice, as you'll see. Okay, so we'll do some case examples. We'll first just start off by getting to naive Bayes through the Bayes optimal classifier that we were talking about last time. Okay, so let's briefly review what we did towards the end of last class. We said, well, we'll be talking about the classification problem where we have to construct a prediction rule. So some rule f, which maps input, which is features corresponding to every data point. So every data point here is an email. Features might correspond to counts of different types of words in the email, or how many people the email is addressed to, and so on. So you can generate a bunch of features for every data point. That constitutes your input. And there's an output space of labels. In this case, say it's a spam classification problem. We just want to classify every email as it's spam or not spam. Right? This is an example of a binary classification problem because the label can take only one of two values. Okay, so we can assign it pretty much a 0 and a 1 to whether it's a spam or not spam. And we call this a binary classification. And we also talked about last time that we have to have a performance metric in mind. And for classification, we take that to be the loss function we take to be the 0-1 loss, which says if your prediction agrees with the true label, you get you don't suffer any loss. So the loss is 0. But if it doesn't match, then you suffer a loss of 1. Right? And we also talked about that we care about finding the predictor f, which minimizes not just the loss, but the expected value of the loss function, because you need to be able to do the prediction well for any randomly drawn test data x. So if I give you any random email or its feature representation x, then we want you to be able to predict its value well. So what we care about is really minimizing the expected value of the loss function, where x is any random draw from some underlying distribution. Right? And of course, the corresponding label y as well. And we talked about how if we plug in for loss, the 0-1 loss function, then our expected loss is just the probability of error. It's just the probability that your predicted label f of x does not match the true label y. Okay? So everybody okay with the setup? Right? We talked about this last time. And we said, well, let's talk about assuming we knew the distribution pxy from which our emails are being generated from. Of course, it's completely hypothetical at this point. We haven't specified what that distribution is, nor will we ever know it in practice. What we'll have is examples of labeled emails. And later, we are going to use those to estimate this distribution. But for now, let's say we have access to this distribution. And we just want to understand what's the best possible classifier that will minimize the probability of error. And that's what we called as the Bayes optimal classifier. Right? So last time we looked at this. We said that the Bayes optimal classifier is just the one that minimizes the probability of error. And we also argued why that classifier is simply the one which, for any given email or its feature representation x, assigns the label which is most likely to occur. So nature chooses a y. We construct a predictor f, and we predict f of x. Right? And the best predictor is the one that sort of matches the nature in the sense that it, for example, if we have an email whose feature lies here, then because we know these are the actual probabilities of the email being spam or not spam, which Mother Nature chooses, we want to be able to predict the same as she does, right? Essentially, so if she has a higher probability of saying red, which is, let's say, spam here, then we would also want our predictor to say spam. So intuitively, it makes sense that the best predictor is the one that just matches that natural choice, for it just picks the label, whichever label is most likely to occur for that email. Right? So intuitively, I hope it makes sense. We also talked about you can think of it mathematically by writing the expression out for this and looking at it, but it essentially boils down to the same thing. All right. Then we also talked about how you can use Bayes' rule to rewrite the Bayes optimal classifier instead of writing it as the classifier which achieves, or basically the output that achieves the maximum probability of the label given that email. We can rewrite it in terms of the class conditional density, right? So instead of the original classifier, which was specified in terms of P of y given x, we can rewrite it in terms of P of x given y times the class prior, right? And we did this using simple Bayes rule. Okay, so hopefully again everybody was comfortable with that. At least if you didn't remember Bayes rule in last class, you were able to go back and refresh your memory about what that is. All right. So we said, well, what do we gain by looking at this equivalent representation of this Bayes optimal classifier is that now we can think of ways our data might be modeled. So we might say, well, all emails that have a particular label, say they are spam or not spam, we can talk about how they might have been generated. What's the probability of getting an email that we know is actually a spam? What does its distribution look like? We can make some modeling assumptions about it, how our data was generated, and then try to look at how different modeling assumptions give rise to different classifiers. And last time we started out by talking about one such assumption we can make on what our distribution might look like for each class, right? And let's talk about that, which was the Gaussian distribution, right? So basically what I wanted to say is the reason we would want to look at something like this instead of this is because now we can, this is known as a generative version. You are able to model how the data, the email, might have been generated or might have been distributed, how the emails are distributed, given that they are spam or not spam. Okay? And we can impose different models on it. And in fact, we started talking about this particular model last time, which is just assuming that for every email, every class, spam or not spam, the email is generated, say, according to a Gaussian distribution. Whether that makes sense or not, you can think of other generative models. Maybe a Gaussian one is not the best one, right? But different models you assume for your data generating distribution will lead to different classifiers. And let's see what the classifier is corresponding to when you assume a simple Gaussian class conditional density. Okay, so if you're still trying to follow this, I think last time we said something like this. We can think of points from one class. And let's do just the 1D problem first. I think last time we even drew the 2D version. But in one dimension, we are just saying that say we have emails that are spam. They tend to be similar looking in some sense, at least the features we have constructed. For example, how many people does an email target? That could be one feature. Then all of them tend to target maybe a higher number of people, whereas regular emails maybe don't target as many people, so they lie along here. Right? Or actually, in a 1D, I should have really drawn all of them exactly on the same line. So let's say we only have one feature. This is the value that each email takes for that feature. And we have some that are these ones that are spams, these ones that are not spams. Right? And of course, they are not going to be as clearly separable as I have shown them. So maybe there's some mixing, right? Something like that. But now we can say that given each class, we can assume how, so given each class means you ignore the other labels. So let's only focus on the x's right now. And we can assume some distribution that might have generated that. And a simple model is a Gaussian distribution. So we say, well, the peak maybe is somewhere around here, right? So that's a Gaussian fit maybe for this, for the spam data. And we can assume something similar, another Gaussian, which clearly in this case should have a different mean, possibly a different variance, for the not spam emails, right? And now we can talk about what, under this Gaussian class conditional density, we can look at what the Bayes optimal classifier is, right? All you have to do is take the class conditional density and multiply it with the class prior, which is the prior probability of the class appearing. What's the prior probability that any email is spam or not spam, right? So we said last time, well, let's think about, suppose there's equal probability of an email being spam or not spam, which is not true, but let's assume that's the case. Then all you have to do is you have to compare this, which is the probability of x given y is spam, which is this curve, to this curve, which is the probability of x given y is not spam, and see where they are equal, right? Or in fact, the base optimal classifier says wherever 1 is higher, you predict that. So bean spam is higher everywhere to the right of this point here, right, where they cross. And probability of x given y not spam is higher here, right? So basically, the decision rule is simply that this is the point they meet. So any email that falls to this side, we'll call it a spam. Any email that falls to this side, we'll call it a not spam. Right? That's the base optimal classifier. Does that make sense? Now, you can have different way these data can appear, right? And based on that, you can have different means possibly for the two classes, and you can also possibly have different variances. These Gaussians don't have to look alike. Some can be squished, others can be fatter, right? And depending on that, your threshold is going to move, right? Yeah, I have a question there.
The red and the green curves, they're a little lumpy. Is that supposed to be like an empirical distribution, or should those be perfectly smooth Gaussian things?
Well, they are Gaussian as well as I could draw them using PowerPoint. Yeah. Yeah, so if they look non-Gaussian, that's my drawing inabilities. Yep. Yep. And actually, I drew one higher than the other to basically point out the fact that here we just talked about having equal class priors. But if you don't have equal class priors, say the emails without spam are more likely than the emails that are spam, then you basically have to multiply or scale up these class conditional densities by the corresponding probabilities of each class, right? So then again, your decision boundary will move because one of these things is going to get pushed up, another one is going to get squished down a little bit, right? So your decision boundary is going to move again. All right, and we'll actually release a set of online questions later today that you can go and perform, which is just like going to be a short multiple choice questions. And one of the questions that will hopefully survive, and I can tell it to you right now because you can think about it, is do we always get a single threshold as the decision boundary in one dimensions if we assume a Gaussian class conditional density? Okay. So think about what all are the parameters here that we can change. There's a mean corresponding to each class, and there's a variance corresponding to each class, and that can change, right? The means can shift, and the variances can be fatter or thinner Gaussians. And depending on what, for all choices of those parameters, can you ever end up with some other sort of decision boundary? Don't give me the answer right now, if that's what you're trying to do. Yeah, so I just want all of you to think of that on your own. Okay. All right, but let's talk about the 2D case, which we did last time. So yeah, just so everybody knows, I haven't formally defined it, but decision boundary is the set of x's for which you have equal probability of each label appearing, right? And wherever you have higher probability, you give that region, every email that falls here has a higher probability of being spam, so you assign it a spam, right? But these are the set of emails for which you have the probabilities exactly match up, and that will be our definition of the decision boundary, right? So you can actually get it from the base optimal classifier. It predicts the value which has for which the probability of that label is most likely, and the decision boundary is simply where the probability for the two classes agree, right? So maybe we should at least write it down formally. So decision boundary for at least a two-class problem is simply the set of x's for which probability y is, say, 0, given x is x, is equal to probability y is 1, given x is x, right? And so for this 1D problem, it was just that.
When you have equal weight,
I wrote probably y given x. If you write it in terms of p of x given y, then you have to multiply with the corresponding class priors. Yeah, right. But that's an important point. Yeah, you don't just so. This is the right formula for the decision boundary, or if you want to write it in terms of p of x given y, then it's p of x given y is 0 times the probability of that prior probability of that class equal to this. These are both equivalent definitions, but you do have to make sure you keep the class probability in mind if you are working with the p of x given y version. All right. All right, so what happens, we can do the same thing for higher dimensional settings where you map every email not just to one number, but to say 2 numbers or possibly higher, a feature set, right, corresponding to say how many people the email goes to or the counts of different words in them. And you can similarly make a similar assumption there. The class conditional densities in this case are going to be, say you have 2 features, are going to be 2-dimensional distributions, right? So x now is a 2D variable. Excuse me. And you can still make it a Gaussian assumption. You just have to use a multivariate version of the Gaussian distribution. So if you have forgotten how that looks like, this is the expression for a general d-dimensional Gaussian variable where your mean vector now is given by mu y. And the mean is, of course, indexed by y because it's going to be different depending on which class you are in, right? So y indicates the class. And you have a covariance matrix, which is sigma y. So that's the covariance between all of the d features. So it's a d by d matrix, right? And yeah.
Can it be only used when x is continuous?
Can this only be used? No. So you can define, these are just examples. You can define whatever distribution makes sense. So if you have a discrete setting, you could use, if it's just a single feature, you could use a binary, just a Bernoulli distribution, for example, or you could use a binomial distribution and so on. So depending on the setting, there are many other distributions you can use. And this is not specific to only continuous distributions. Right? Yeah?
So what happens on the decision boundary? What do you classify?
Oh, what do you say? You can randomly say output one or the other, right?
So your classifier is not actually a binary function. It's a function that outputs a distribution sometimes. At least on the decision boundary. And in theory, you could also generalize it to have.
It's still okay. So you can have classifiers. Right now, we are saying classifiers are going to output a predicted label f of x, right? We could also output a distribution. We haven't talked about that. Here, even at the decision boundary, you are still outputting one label. You are randomly picking a label to output, but you're still outputting one label.
You could do it deterministically.
You could even do it deterministically. Yeah, you could say that everything on the decision boundary assign it to, class 1. Doesn't matter. That's not going to change your overall performance. Right. So that's a good point. Any other questions? Okay. So here's one example of assuming class conditional densities that are multivariate Gaussians, in this case 2D. So you should think of points here as we did last time. So now here are a bunch of points in 2D. Emails of one kind, emails of another kind. And we are fitting Gaussians to them. Again, we are fitting a mean value and then a covariance around it, right? And covariance, you should think of as when we draw a circle here or an ellipse, that's just a level set of the Gaussian distribution. So in 2D, it's going to be a 2D bump. And when you take a slice through it, right? So a circle or ellipse here represents points that have the same value of the probability density, right? So all these points have exactly the same p of x given y. Right? So that's what you see here. In fact, concentric circles represent, or concentric ellipses represent different points where the probabilities values take different values. So these are just contours of your density. Everybody okay with that? Right? So you can see that how this sort of reflects variance. So we can draw, this is the mean, and around it we can draw different concentric ellipses. And we can do the same over here. Right? And in this case, in the first example, we actually have the same covariance structure to both classes. I think last time we talked about it being the identity, which means that your features are uncorrelated, right? But in this case, we have shown them to have some correlation. But it's the same for both classes. That's not necessarily true. You could have different distribution for the two under the two classes, and you might want to model it using two different covariances. And the question is, what kind of decision boundary does that lead to? And can people argue why? I think we briefly said it last time, why it's linear in this case when they have the same covariance. So let's go back and think of the definition of the decision boundary, right? It's where these two, the probability of each label is actually equal, right? which if you wanted to think of it in terms of P of x given y, then it's given, you have to think of the class conditional density multiplied by the class prior as being equal. And what I've drawn here is actually the capital P1 represents probability of one of the classes, and P1x represents the class conditional density. So this is already the product, let's say. Okay? Or if you don't want to think of it that way, just think that the class priors are the same. Then the decision boundary is just when one Gaussian is equal to the other Gaussian, right? Or the values of the two points for which the values under the two Gaussian distributions are actually the same. When does that happen? You should be able to convince yourself that that happens along a line when the covariances are the same. Can people think of why that's the case? Right? All you have to do is, let's apply this, right? We have a form for P of x given y right there. It's a multivariate Gaussian. Let's assume equal class probabilities, that helps. And then all we are saying is we are equating this. There's a common covariance, so I'm dropping the subscript y, right? I can just write it as sigma. This is common covariance. Okay, maybe I should write bigger. Can people in the back see? I'll try to write larger next time. Yeah, maybe not. Okay, that's common covariance. Let me bring this up, maybe, like that. And then we have the exponential term here. The means are still going to be different under the two classes. So this is the mean under class 0 times sigma inverse. Again, I'm dropping the subscript times x minus mu1, or that's still mu naught, sorry, over 2. Yeah, transpose. And we just want to say for what points x is this equal to the value of the probability under the second class, which is just the same expression, except we replace the means mu naught with mu1. Oh, sorry, again here. So all you have to do is equate these two expressions, right? That's actually fairly easy to do. The stuff in the front drops out. The exponential terms are similar, so you can just look at when this exponent agrees with this exponent. These are two quadratic terms, right? You can open it up. You see that the part that's quadratic is just x sigma inverse x transpose, right? And that's the same on the other side, right? So all this boils down to is just looking at when is this equal to that, right? And you can clearly see that because the sigmas are the same on the two sides, the x transpose or x sigma inverse x transpose, which is the quadratic part, drops out on both sides, and you will end up with a linear equation, right? Which says that the set of x's for which the probabilities agree is just a line. Everybody okay with that? Right, and if they have different covariances, you can also see that now these sigmas would have subscripts assigned to them, and the quadratic terms are not going to cancel on each side. So you actually end up with a quadratic boundary. Yeah, there was a question here?
I just want to ask where is sigma y, but in theory, both sides are the same.
That's exactly what I said. So you get a linear decision boundary when the covariance matrix is the same under the both classes. So sigma y is just indicating the variance for class y. And since it's the same under both, we call it sigma. All right? Yeah. In the case of Gaussian, is it if and only if? That's a good question. What do people think? Yes? No? Did I see a no? That could be the case, but even in that case, it's not going to cancel out, right? You really need the quadratic terms to cancel. Yeah. Yeah, I believe that's the only case. I think the answer is yes. So it is if and only if.
In the limit as sigma inverse goes to infinity, right? Then it.
Yeah.
Or as sigma
then,
goes to infinity, sigma inverse goes to 0.
Yeah. Right, of course, except for pathogenic cases like that, where, yeah, Okay, yes.
This is assuming that both the prior probabilities are the same, right?
This is assuming the prior probabilities are the same, but even if they are not the same, you see that that actually only leads to a constant term, right? So the answer does not change. Because then you'll have some pi naught here, pi 1 here, let's say, two constant numbers, right? But they are not dependent on x. So in fact, we can try to do that. That's just going to be another constant, right? So I can have, say, for example, right now I just have 0.5, 0.5, say, on each side. You could have 0.1 here, 0.9 here, right? And because the quadratic part is in the exponent, when you are now going to try to relate the two sides, you can take a log. That's a simple way to do it. Then this thing, it will just become log of this minus the quadratic part. And log of 0.9 minus or stuff, this stuff I guess cancels out, so you don't have to worry about that. Yeah, so it's log 0.1 minus this quadratic, log 0.9 minus that quadratic. So the two log parts are just a constant. It's not dependent on x, so it does not change the shape of your decision boundary. What does it do though? It shifts it exactly, right? So if the class probabilities are different, if they are equal, then it exactly, the decision boundary passes through the center. If one class is more likely to happen than the other, then the decision boundary moves away or towards it? Away from it, right, yes. That could make another interesting online question, actually. So for those of you who didn't get it, you should try to think of why that's the case. All right, everybody okay with that? Did you get this? So this is all we've talked about so far is what's the best possible rule, right? And how does its corresponding decision boundary looks like. So in this case, the best possible rule, if you assume that your data is generated according to a Gaussian distribution under each class, simply says everything to one side of this line is one label, everything to the other side is another label. In the case of different class covariances, you actually get a quadratic decision boundary, right? So you can already see how, as you're changing the parameters of your problem, right? In this case, in some sense, the parameters are simpler because they are coupled between two classes. Here, you have made the parameters different, and so you're already making your classifiers more complex because the corresponding decision boundaries are more complex, right? Using such similar covariances, you can only hope to classify data that's linearly, that can be separated well by a linear classifier, but here you're able to do quadratic, so a more complicated data sets, right? And you'll see this in general. As we are going to increase the complexity of our classifiers, we will be able to handle more complex data sets, but of course, we'll talk about certain other issues that come up there, right? Okay, any questions on this part before we move further? Yeah.
So the Gaussians is something you made up, right? I mean, you decided the Gaussians.
Exactly. And you can, as somebody asked, like this is the case, you can do this for continuous features. What if your features are not continuous? I mean, even for continuous, you can use another distribution. It doesn't have to be Gaussian. It depends on what you plot your data, see what it looks like. If it's very skewed to one side or the other, it doesn't look like a nice bell, then maybe you shouldn't be assuming Gaussian. You should be assuming some other form. But if your features also are, for example, discrete, then you would need to use another distribution, like multinomial or Bernoulli or something else. So this is just one example. So what you should know is it's not necessary that the Bayes optimal classifier uses a Gaussian distribution. This is an example of the Bayes optimal classifier using Gaussian class conditional densities. But the Bayes optimal classifier is more generally just defined as this, either of these definitions. And you can plug in whatever distributions make most sense for your problem. Yes?
My question is, how do you know there's this only one or two features?
So feature is something you craft. And that's an important part of machine learning is to come up with good features. So you decide how every email is a data point and how you're going to take every email and represent it as a vector of features. That's totally up to you. So you decide what the features should be. And that's, yeah, it's an important problem, but we'll talk a little bit about it, but yeah, not too much. It's more of an art than a science. Yes. Or yeah, Nicole.
We only use one and two-dimensional examples because that's what we can print on
Yeah.
each screen. In reality, in most cases, you have a 20 to 100 to 100,000 dimensional example.
Yeah.
If you can know how to visualize that, yay.
Yeah.
And there could be some kind of situations where we don't know some dominant factor that you didn't take out.
Yeah, you're saying some important feature that you missed. Sure. Yeah, definitely. And yeah, when you're going to apply these things in practice, you would never assume just as Aarti pointed out, never use just one or two features. That's just for visual purposes and understanding it easily. But you will be dealing with many very, very high dimensional problems usually. Right? In fact, we talked about one like the brain imaging data sets. Usually they represent every image as basically the value at every voxel, which is one of the pixels if you want to think of it as in the image. So it's as many pixels as there are in the image. That's the dimensionality of each image. Right? That's how many features you're representing each image by. So it's a very high dimensional problem. And most problems you will encounter are going to be high dimensional. And in fact, the whole field of machine learning in the past few years has moved towards addressing these high dimensional problems. And we'll touch base on some of them in this course. Or at least some modifications you need of current methods to handle high dimensional data. Right. OK, any other questions? All right, then let's move forward and let's talk about now learning this optimal classifier. So far I've told you, well, you somehow know these distributions, or you can assume them as we did here. Right? You assume you know the parameters, you know the means, you know the covariances, everything, and you have your best possible classifier. Right? Now let's talk about how would we learn the best classifier, even if you assume a form for it. Right? So say you have assumed Gaussian class conditional densities, but you still don't know what the mean and the covariances are. So you should be able to estimate these from data that's given to you. And how do we do that? All right. So you can see that to learn the Bayes optimal classifier, again, here are the two forms in which we can write it. We need to know two things. One, we need to know the class prior, and we need to know the likelihood of your data for each class. Right? And you need to basically know these probability tables, if you want to think of it as, for all x and y. All possible values that your feature can take, and all possible values that your classes can take. Right? So let's start with an example just to get a sense of how many parameters do we need to estimate to find our Bayes optimal classifier. Okay, and we'll actually do a discrete case now. So let's consider the task of predicting whether or not a picnic spot is enjoyable given different features. So here the features are like sky, what does it look like, sunny or rainy, temperature, what does it look like, warm or cold, humidity, normal, high, so on. Right? So we have here 6 features, and they're all binary, as you can see. So they have just 2 values. Of course, some of them can take more, but let's just, for simplicity, say they can take 2 values. And your label is just whether you enjoyed the spot or not. And you can collect a bunch of such data. So we can have n such examples, which say what the current setting for these parameters was, not parameters, but features was, I should say, and whether the spot was enjoyable or not. So now let's think about how many parameters do we need to estimate to learn. Well, to learn the Bayes optimal classifier, we need to learn P of y given x, or these 2 things, right? How many parameters do we need? So first, let's focus on the prior. How many parameters do we need to learn the prior probability of a class in this simple example? Just one. Why? Yeah, you only have 2 classes here. The answer is either the label can be yes or no. So you assume one parameter that says the probability that given any picnic spot it's enjoyable, and the one that is not enjoyable is just 1 minus that, right? So in this case, you have 1. What if you have k classes? K minus 1, right? Okay, so if you have k labels, then you need k minus 1 parameters just to learn the class prior. This is actually usually the easier part. What about the likelihood of your data under each class? So in this case, we have binary features, and let's say d of them. Then how many parameters do you need to learn? Yes? 2 to the d minus 1 for, yeah, why is that, first of all? Right, so we have d features, and each of them can take any of 2 possible values. So the total number of possible values your features can take is 2 to the d, right? But you need, why did you say 2 to the d minus 1? yeah, again, you can assume probabilities for all possible assignments out of this 2 to the d except for 1. The last one will be just 1 minus the sum of the remaining. They all have to sum to 1. The total probability has to be 1, right? So it's 2 to the d minus 1, but that's for one class, right? So for the, what's the total number of parameters? That's just 2 to the d minus 1 times the number of classes, which is k in this case. So that's how many parameters you need to learn if you're given these d binary features. And you can already see the limitation here. As we are going to encounter more and more features, the high dimensional case you just mentioned, right? This number is exponential. It's 2 to the d in the number of features. So you have to learn a humongous number of parameters to be able to learn your Bayes optimal classifier in this simple binary feature setting, right? So that's very, very expensive because, as you can imagine, if you have to learn even single parameter, say we are tossing a coin, right? And we want to estimate what's the probability that it falls head or tails. How many samples do you need? Samples is just the flip of a coin. You are actually going to take the coin. You don't know what its bias is. How likely is it to give a head versus tail? You're going to take the coin and you're going to toss it multiple times. You're going to look at the output. You need to see more than one example to be able to estimate a single parameter, just the bias of that coin. Now we have 2 to the d parameters. So how many samples do you need to be able to learn that? That needs to be to scale accordingly. So the number of training data you need to be able to learn this Bayes optimal classifier well is very, very large because it scales exponentially in the feature size. Yeah. Excuse me. So what can we do to get around this assumption or around this requirement? This is just a summary of what we talked about now, that we need number of training data to be much larger than the total number of parameters. And that's an issue. So what naive Bayes does, which is a classifier we are going to discuss next, so far we've talked about the Bayes optimal classifier. The naive Bayes makes an additional assumption that helps simplify this requirement. Okay, so instead of requiring a lot of training data, you can actually train naive Bayes using much smaller number of training data. And the reason is because it assumes something called conditional independence. Okay, so this is something, again, hopefully you're all familiar with. It is one of the prerequisites, but do people know what conditional independence of 2 random variables is? Anybody who does not know? How many people know it? I still see some hands missing. All right. So I'm assuming most people know it, but as a quick reminder, it says that, so independence, I hope everybody knows, right? 2 random variables are independent means that their joint probability is just the product of their probabilities, right? They don't depend on each other in any way. The outcome of 1, 2, if I take 2, let's say, coins and I toss them, then the outcomes are independent, right? There's no way one is influenced by the other. But maybe if I take another coin, I flip it, and then based on its outcome, I decide which one of the other 2 coins to pick, and then toss them, then things might be different, right? So that's the idea, essentially. That 2, I hope you get that if 2 variables are independent, then they're just like, their outcomes are completely not dependent on each other. Conditional independence means that if x is conditionally independent of y, it means that given z, we also have to specify given what when we are doing the conditioning, then it means that given z, x, what's the outcome of x does not depend on y at all, which means I can actually drop it from the conditioning. So this probability of x given y and z is actually the same as the probability of x given just z. Okay? So it's saying it doesn't matter, once you condition on z, x becomes independent of y, you can actually drop y from the conditioning. It does not play any role in specifying what the outcome x is. And equivalently, you can also write it as p of x and y given z just factorizes into p of x given z and p of y given z. You can simply use the definition of the and probability of x and y here to go from this to this, or vice versa, right? And here's an example of that. If we say whether thunder is independent of rain given lightning, well, first of all, you can just think about, are thunder and rain independent? Probably not, right? Thunder and rain usually happen together. so they're probably not independent. But given lightning, are they independent? It makes sense, right? Because whenever there's lightning, there is thunder, whether or not there's rain. That's usually the case. So thunder and rain are conditionally independent given lightning, but they are not marginally independent. Does that make sense? All right. So as I emphasized earlier, it does not mean that thunder is independent of rain, just that given lightning, you don't expect thunder to have any relation to rain. Here's another example, which is similar to the coin tossing example I was talking about, that say C thinks of a number and calls A and B separately and tells them what number it has thought of between 1 and 10, right? And due to noise in the phone, A and B each independently draw a conclusion about what the number was. Okay? Now, A thinks the number was NA and B thinks the number was NB. Are they marginally independent? NA and NB? What do people think? So the setup is this. C thinks of a number, calls up two friends, and tells them what the number he thought of is, but there is disturbance in the lines, which are complete, they are two independent lines. And so A and B think that the number was, they could have different opinions about what the number was. One thinks it was NA, another thinks it was NB. Are these numbers marginally dependent, independent? Yeah? No? Why is that? Yeah, you expect them to be related. Ultimately, they both heard the same number, and even though there was some independent noise, it's coming, they started off from the same point, right? So you expect that their outcomes are going to be dependent. So they are actually not marginally independent because, yeah, given, if I tell you what one guy thought the number was, you get some idea about what the other one should be, right? Are they conditionally independent? Now, if I told you what the number C actually thought of was, now what's the randomness because of? If I told you what n is, if I condition on knowing n, then the randomness is purely due to the independent noise in the telephone lines, right? So these two things are completely independent of each other now that you know n. All right? So hopefully you could relate to one of these two examples to understand conditional versus marginal independence. Okay. Any questions? Yeah.
What is the definition of marginal independence?
Just that the probability of the two random variables is equal to the product of their individual probabilities. So probability of A and B is probability of A times probability of B. Right? Yeah, and the difference is, as you can see here, I mean, the definition actually extends. So if I did not condition, that's your marginal independence. And if this statement holds with conditioning on some variable like z here, then we are talking about x and y being conditionally independent. All right, so how can we take this idea of conditional independence and use it to help simplify how we can learn the Bayes optimal classifier? So here's the naive Bayes assumption, which is what the naive Bayes classifier is built off of. It assumes that the features are conditionally independent given the class. So what that does is, here are two features x1 and x2 for one class, say all emails that are spam. And it says that you can write this joint distribution as just the product of two one-dimensional distributions. Okay? And more generally, it could be the features. So we are just writing the joint probability of all of them as the product. And let's see how that simplifies things now. So first of all, it's an assumption. It may not hold in practice. But that's what naive Bayes classifier is assuming holds true. Or at least that's what it's modeling. Even if your true data does not have to follow it, but that's how the naive Bayes classifier is going to be derived. Now let's think about how many parameters do we need to estimate if this additional assumption held. So remember how we counted the number of parameters? We said how many parameters do we need to find out two things. One was the prior probability of the class, and another was p of x, which is actually x1 to xd given y, right? So the first one, of course, does not change. But the second one, the likelihood of each data under each class. Now, why does that change? How many parameters do we need now? Say these are binary features to learn this. If you remember earlier, there are d features. So we said there are 2 to the d possible values they can take. Each can take yes or no, or sunny or rainy, and so on. We needed 2 to the d minus 1 because they all have to sum to 1 times. For each class, we needed that many parameters, right? So this was the number of parameters we needed earlier. What happens now? If we can rewrite this as the product of individual marginals. Yeah, go ahead. Let's say for one class. Let's say for one class first. So d is the number of features. D is the number of features. The number of classes is how many values y can take, right? So let's say for one class, there are d features. How many parameters does that imply? Yeah, d or d minus 1, because they can still sum up to 1, right? Yeah, so it's.
No, it's d, not d minus 1.
Oh, it is d. Yeah, because they are they're independent. Sorry, it is d. You're right. Yes. Thanks.
Times 2 minus 1.
Yes. Yeah, thanks. It is d. Yep. So we have d, and actually, I didn't have to write 2 minus 1. It's d parameters because every feature is binary. So for every feature, you have to specify one probability, and the probability. So for example, xi means sunny. You can take that to be one parameter, and then the probability that it's rainy will be 1 minus that, right? But you do need d parameters for each feature, and it's d per class, so it's total d times k. So instead of 2 to the d, which was before, with the naive Bayes assumption, we have brought it down to d times k, which is very, very small. So this is saying you can train a naive Bayes classifier with this extra assumption using only the number of training data you will need, only need to be more than d times k now. Right. Okay, so here's the naive Bayes classifier. You need to assume what the class prior is, so you need to assume one parameter for that. You need to have d, the assumption is that there are d conditionally independent features given the class, and for each feature we are going to have a likelihood that we are going to now assume that it basically, the joint likelihood factors into these individual likelihoods. So all we need is, for every individual feature, we need the p of xi given y, not p of the whole x, x1 through xd given y, right? And so our decision rule, which is what this was the Bayes optimal classifier. The naive Bayes version of it is simply the one that replaces this joint distribution with product over the marginals. Okay? So that's just the decision rule. It's simply taking that joint distribution where you were modeling all the features simultaneously and writing it into product of 1D distributions. Okay?
So what's the meaning of likelihood? What's the difference with probability?
It's similar. We usually use likelihood when we're talking about probability of data under a given class, right?
The other thing is that often when we say likelihood, we're considering it as a function of parameters, and probability when it's a function of the data. You can consider it either way. It's the same function, but it's emphasizing one over the other.
Right. So likelihood, yeah, likelihood, as Jeff said, typically emphasizes that you have dependence on some parameter. You have certain model for your distribution, and it's, yeah, that's partly true. But I mean, yeah, like non-parametric settings, it might be hard. But
like every word, right? The meaning is
yes. Yeah, but in machine learning, we use likelihood often to mean that. All right. So what you should remember is, even though we obtained it from the Bayes optimal rule, this was the definition of the Bayes optimal rule, and this is the naive Bayes version. The naive Bayes version, naive Bayes classifier may not be the optimal classifier because it's making this extra assumption. Only if that assumption actually holds in practice can you claim that the naive Bayes classifier is going to be the optimal classifier, but not in general. Okay? So you might still make this assumption and build a classifier like that, but it may not be optimal for your data unless your data actually satisfies this assumption that every feature, which is a strong assumption, right, that every feature does not depend on each other. Often the features you will construct tend to be dependent, right? So how do we actually train a naive Bayes algorithm? Of course, we wrote it that in the sense that it does factorizes, joint distribution factorizes, but we still haven't learned these parameters, right? We need to learn them based off of data. So how can we do that? So say now we actually have examples. So I think the notation might get a little complex, so first let me explain that. So we have n examples, and we'll denote superscripts to denote which example we are talking about. But every example, so the different examples are, for example, different emails. But every email can be represented by a collection of d features, which are the superscripts here, x1 through xt. So the jth email has 1 to d features. All of them have d features, but that's the representation we'll use. And again, this notation might change from class to class. So we assume that in 701 you have enough maturity to be able to associate what the different symbols, whether they're superscripts or subscripts, might mean in the appropriate context. N will most often represent data. D will often, D or P will represent dimension. But again, we can't say in stone that we'll always follow that rule. We'll try to follow it. But it should be clear enough from context. Okay, so this is our training data. And we want to now use this to learn the components of our classifier, which are the class priors and these individual, I guess we never wrote down here, but the individual distributions for each feature. These things, right? All right. So first for class priors, how can you estimate the class prior given some data? So you want to basically estimate the probability that any given email is spam. How would you estimate it if I gave you some training data? I gave you a bunch of emails that had labels. Yes?
Look at your Y's and just take the distribution of the labels in your training data.
Right. What would the distribution be? Right. You'll just count, right? You'll just say that, okay, I have n emails. How many of them were spam? So my probability of spam is that count, how many were spam, divided by n, the total number. Makes sense, right? So we'll get to the principle behind it in a minute, but hopefully that makes sense. We just estimate the probability of a class by counting. So this hash j just means number of j or number of emails such that their label was little y, right? Spam or not spam, and divide by the total number of emails we have. That's a good estimate for our probability. What about likelihood? We can do something similar, right? At least for binary or for discrete features, we can do that. We can simply count. So the likelihood we need to estimate p of xi given y. First of all, we can write this conditioning as the joint over p of y, right? Just using the definition of the and. And then we can, again, replace each probability in one variable or two variable with the corresponding counts. The denominator is exactly same as this, and the numerator we now count how many emails have the label little y, which could be spam or not spam, and their corresponding ith feature is xi. Okay? Number of people it was sent to is 100, let's say. So in this case, little xi would be 100, and we are talking about the ith feature, which is number of people the email was addressed to. Yeah.
In my training data, I never found it with the xi, so it becomes 0 and the
Yes, so we'll get to that in a minute. That's an excellent point. Okay. Yeah. Oh, just that if you never see a particular feature, then your probability estimate will be 0. Yeah, we'll get to it exactly in a minute. And in fact, as you will see, as you can think of it, you can do the same. We can use these plug-in estimates for the Bayes classifier or the naive Bayes classifier. And you will see that one of them is actually going to run into that issue more than the other. That if you don't see something, you assign it as 0. Right? But yeah, classifiers face that, and we'll get to it. But all right, so what does, so your rule is just going to be this. You estimate your class prior, you estimate your class likelihood, and then you just plug those into your expression, right, here. and you look at when this product for what value of y, spam or not spam, is this higher, right? And that's going to be your rule. So the naive Bayes prediction for a test data x is you just plug in, it's just going to be exactly the expression we saw before, but now with plug-in estimates of your probabilities. Make sense? So that's just the naive Bayes classifier. You count how many times a particular feature and a particular class appeared. How many times did you have emails spam that were sent to more than 100 people? And you're doing those, plugging in all such estimates, and then just forming your Bayes optimal classifier like this. All right. All right. So we'll talk about, there are two issues that come up with this naive Bayes classifiers. Of course, the nice thing about them is you don't need as much training data to train them because you have fewer parameters. But one of the issues is that it does rely on this conditional independence assumption, which often does not hold in practice. So what's the implication of that? So you still run a naive Bayes classifier, but your data is actually dependent. Then your actual probabilities, right, the p of y given x's, they're going to be biased towards either 0 or 1. And why is that? As an example, think of the completely dependent case. Suppose you had two features that are exactly the same. That's an example of extreme dependence, right? Complete dependence. Suppose you just replicated one feature twice. That should not change your classifier, right? Ideally. But because of the naive Bayes assumption, the naive Bayes is assuming that every feature is independent of the other given the class. But if you just replicated one feature, why do you think your estimated probabilities are going to be biased? Because what we are doing is, say we have two features. Let me use another paper here. So we have two features, x1 and x2, and they're actually just the same. They're just x, right? Then the Bayes optimal classifier is going to use p of x1, x2 given y, right? Which is actually just p of x given y. But the naive Bayes classifier is going to write it as p of x1 given y times p of x2 given y, right? Which is p of x given y times p of x given y. And because probabilities are less than 1, you can see that now we have this value is going to be smaller than this value. So it's going to be biased towards smaller and smaller values. So biased towards 0. You can actually get the other kind of bias if there are variables that are perfectly negatively correlated. So one is the inverse of the, not inverse, but like if one is 0, the other is 1. Right? So if you have those kind of negatively dependent features, then you can end up with, again, your estimated probabilities being biased towards 1. Okay? So this is a limitation of naive Bayes, that if your features actually happen to be dependent, then your estimates are going to be off. And so your decision rule is going to be off. But still, I wanted to say that it's actually one of the most used classifiers and actually works very well because of the requirement that it can handle, it requires very few training data. So when you have a lot of features, having the ability to train such a classifier with few training data actually helps you quite a lot. Okay, so that's one of the issues. The other issue, as somebody pointed out, is insufficient training data, even for this setting, right? So what we mean by that is that there are certain features you may never see. For example, so here our class label is that it's a spam. And one of the features was whether the word earn appears in it or not, right? But it might happen that the training data set I give you never has any spam email with the word earn in it. It seems like a good feature to use, but the training data may not have it, right? Then what happens to our estimated probability that x1, your feature is that earn appears? The estimated probability is just going to be 0 because you're just counting, right? You're counting how many times a feature appeared with a particular class, and you're plugging in those counts as your estimates of the probabilities. So your p hat of x1 is going to be 0. Right? You might ask the question, well, why do we even include it as a feature then? Because it could appear in one class and not the other. That's also possible, that spam emails may not have them, but not spam emails could have it. So you come up with, features are something you come up with a priori, right, on your own. So you have a particular feature, but it just happened to never show up in an email with spam in your training data set, and so you estimated the probability to be 0, then no matter what the values of all the other features you might have crafted are, just because you did not see this one feature ever in your training data set, you will output the total probability to be just 0, right? Because it's a product of all these probabilities. So even if you don't see one of them, you're going to output a 0 as your probability, right? So this is an issue. And let's see what we can do about it. So how is it usually fixed? To understand that, let's actually revisit, well, what's wrong here? What seems to be wrong is that we were using these empirical counts as estimates of our probabilities. So we need to fix that somehow, right? So one way to fix it, and actually before we get to that, let's revisit empirical counts first and see them from a more principled perspective. So we'll see that empirical counts, which sort of seem natural, well, if you have to tell you what's the probability of an email being spam, I count how many emails are spam, given the total number of emails you have told me, right? That seems a very reasonable approach. But you'll actually see that that is actually nothing but the maximum likelihood estimate under a particular model for the variable, whatever is the label, spam or not spam. To see that, here are a bunch of emails, right? And say that's your training data, and you have corresponding labels, spam or not spam. Then what's the underlying model for which just empirical counts is actually a good estimate? Here's the model. It says that, let's say the probability of spam is theta, probability of not spam is 1 minus theta, right? And we are assuming that the labels here are all IID. Means that IID means independent and identically distributed. So they are all independently drawn. The label of every email is independently drawn, and they are identically distributed according to a Bernoulli random variable. So with a certain probability, it's theta or 1 minus theta. Okay? So this is actually the underlying model, and we'll see that under this model, the empirical counts actually turn out to be the natural maximum likelihood estimates. So we'll talk about what that means in a minute. But I hope the model is clear to everybody. Right? We're just saying that you flip a coin to decide whether an email is a spam or not spam. So that's your model. All the labels are just generated IID according to a Bernoulli with theta as the parameter. And the maximum likelihood rule says that the theta that maximizes the probability of observed data is what should be your estimate. So theta is a parameter. For whatever setting of theta, you get the maximum probability of your observed data. That's the theta, which is your maximum likelihood estimate. All right? So let's derive what that is when we know that our data, D, which is our data, this is all the collection of all labels, is drawn from a Bernoulli theta distribution. And we'll see that you will just end up with the empirical counts. Right? So let's do that. Here's again our MLE rule. And we are going to look at what's the probability of the data given a particular parameter, theta. Okay? So what's our data? P of D given theta is nothing but the probability of y1 to yn given theta. And actually in my notes I might have x's because that's what I was using somewhere else. So you should replace these x's with y's, because I was doing it earlier for an example where you're just tossing a coin. We're talking about labels now, so let's use y's. Right? And why can I write it like this? So in that step you see I've written it like this. So why is this first step valid? Because we said that all the yi's are drawn independently. They are all independent draws, right? And this is the joint distribution. This is just, if the events are independent, it's just a product of the marginal distributions, right? I hope people get this, just from independence. Now what is P of xi given theta? What's the probability of a label? It's just, we know they are all identically distributed, right? Just from the Bernoulli theta. So each probability is just theta or 1 minus theta depending on whether it was a spam or not spam, right? That's the Bernoulli coin flip model. So I can break it up into data points I such that yi is spam, and then I just have a theta here. and product of I such that yi is not spam, and I get 1 minus theta. Right? So another way I can write this is I'm just taking theta and multiplying it as many times as there are spam emails. So I can instead write it as theta raised to the number of spam emails times 1 minus theta raised to number of not spam emails. Right? So that's just an expression for the likelihood of our data. And we are calling this likelihood, and again, as Jeff pointed out earlier, you can think of it as a probability, but oops. All right, that's telling me I have to quit soon. But right, so but because it's indexed by a parameter, it's telling you the probability of something indexed by a parameter. That's why we call it likelihood in machine learning often. Right? So this is an expression for our likelihood under this Bernoulli model. Let's see for what setting of theta is this likelihood maximized. Okay? So how do you maximize a function? Yeah, there's a question before that.
Yes, the NS there are the counts, right?
So alpha S is the count of spam email, and alpha NS is the
sub S. Okay.
Yeah, alpha sub S, right? Yeah. Yeah, maybe I could have used something simpler, but that's just the number of spam emails and number of not spam emails. All right. So we have to maximize this expression over theta, and how do we do that? Just take the derivative, right? So let's do that quickly. So if I look at del by del theta of theta to alpha s 1 minus theta to the alpha ns, then the easiest way to do this is actually if you start deriving this thing, it gets pretty ugly. But if you take the log, it's much simpler. And why can we take the log? Because all we care about is not the maximum value. Well, we can also do that, but which theta maximizes this expression, right? And whatever maximizes this also maximizes log of that, because log is a monotonically increasing function, right? So whatever theta maximizes that value also maximizes log. All right, so let's instead do log of this term, which is just log of this quantity is alpha s log theta plus alpha ns log of 1 minus theta, right? And taking the derivative, we get this is alpha s times 1 by theta alpha ns over 1 minus theta, and actually this becomes a negative, right? And let's set it equal to 0. At least when theta is theta hat MLE, this is the maximizer, then it's equal to 0. So we end up with theta hat MLE as we just have to solve for alpha s over theta equal to alpha ns over 1 minus theta, and you'll see that you end up with just this, which is nothing but the relative count. It's saying how many emails are spam, and you divide it by the number of spam and non-spam emails, which is the total number of emails, right? So you just end up with the relative counts. All right, questions? No? All right, yeah.
How do you know not to keep the maximum value, not the minimum value?
So yeah, if you really want to double check it, you should take the second derivative and make sure it's positive or negative. At least that's one way to do it. Yeah. Right. And you should do that. Yeah. So you should convince yourself that you actually this is a maximum and not minimum. Yeah.
Isn't alpha not spam n minus alpha spam?
Yes, that's why I said. So the denominator is actually just n. Right? That's why you end up with the relative count. Yeah. Exactly. So every email is either spam or not spam, and you just end up with n. Right. So this is actually a motivation for why this plugging in the empirical counts makes sense, because it's actually, from a principled perspective, it's actually the maximum likelihood estimate under this model where you assume that every outcome, every label was independently generated according to a Bernoulli distribution, let's say. Right? All right. So, but the issue with doing this, of course, was that if no email was spam, then we output probability of spam is 0. But from prior belief, we might know that spam emails do occur, and we want to correct for this situation, right? So how do we encode? So the reason we believe this is not correct is because we had some prior belief, right? So really, that's what we need to bring in if we want to move our probability estimate away from 0, right? And how do we are we going to encode the prior belief? Well, here's the idea. You just come up with some prior distribution for your parameter theta, okay? We believe that the theta parameter, for example, is most likely 50-50. Of course, this may or may not be the right model here, but you can assume some particular distribution, some prior distribution before you even see any data of this is your prior belief about what possible value theta could take. You think most likely it should take 50-50 value, but maybe it can also take other values with smaller probability. This is just one example of a prior distribution you can throw in. That's just your prior belief about what you think the probability should be. But then you're going to observe the data, and then you're going to change your opinion after looking at the data on what's the probability, right? What's the probability of your email being spam or not spam now that you have seen the data, and that might look skewed. Right? So you start with some prior knowledge. You look at your data, which is the likelihood, and then, as you know from Bayes' rule, you can now compute the posterior, which is related to just the product of the two. Right? We can go from P of D given theta to P of theta given D. And what we are going to do now, maximum likelihood estimate said pick the value of theta which maximizes likelihood of your data. Now we are going to instead say let's pick the value of theta which maximizes our posterior belief in what the value of theta should be, after we have looked at the data and included some prior information into it. So we are going to look at the product of whatever our prior belief was and the likelihood, and we are going to try to maximize that. Okay? So the reason this is different is because you are bringing in, instead of just maximizing likelihood, you are bringing in the prior, and now you're trying to maximize the product of the likelihood and the prior. Okay? So well, what prior belief should you put in? You can, that's really from prior knowledge, so you can use any distribution that you believe is a reasonable assumption on what that, how you expect the distribution of spam or not spam emails should be. But one popular set of priors are known as conjugate priors, and we'll actually use one of them. They are used very often in machine learning, and the reason being that they actually imply whatever form you assume for P of theta, your P of theta given D actually has the same form. So we'll see that it actually has a nice interpretation once you start using conjugate priors. It's easy to interpret what's going on. All right, so at least for our problem where we had the likelihood, we just derived this likelihood, right? Let's look at for that, what can be a prior that when multiplied by this kind of a likelihood yields the same form for the posterior. All right, and these sort of pairs of a distribution and its conjugate prior, they are known. There's a set of them. You can look them up on Wikipedia and so on, but we'll just mention one of them. So if you know that your likelihood has this particular form that we just derived, which is actually a binomial distribution, if you want to go look at it, then it turns out that for a binomial distribution, the conjugate prior is the beta distribution, which means that if I take a beta distribution, I multiply it with a binomial distribution, then I end up with a beta distribution again. And we'll see that actually this has a nice implication in the context we were working in. So here's actually how the beta distribution looks like. It might look pretty nasty, but all you have to remember is what it's saying is that the probability of theta is theta to some number, which is one of the parameters of your distribution, and 1 minus theta to another number, which is another parameter of your distribution, and divided by, this is just a normalizing factor to make sure that this thing sums to 1. Right, so you can pretty much ignore that. So this is a beta distribution, and you can see that when you multiply this beta with a binomial, I mean just based on their forms, what you're going to do is just add the exponents, right? So if I multiply this with this, the power of theta becomes alpha s plus beta s minus 1. The power of 1 minus theta becomes alpha n not spam plus beta not spam minus 1. So you end up with actually another beta distribution where now the parameters, you have basically just added the parameters, you took the parameters of the original prior distribution and just added alpha s and alpha n s to it, right? Yes?
What is the beta essence?
It's just a parameter. So beta distribution has two parameters, beta s and beta ns. These are two parameters of the distribution. But let's look at what its implication is for our setting. So let's look at what this beta distribution, which I just threw out of the hat, looks like. But I hope at least from this slide you understand that what we are trying to do is we were trying to say we have the likelihood and we are going to multiply it with the prior and end up with the posterior, right? And what this is saying is that our likelihood is of that form, it's a binomial. And if I take my prior to be beta, then I end up with the posterior also being beta. Okay, that's the probability of a conjugate prior. And the reason it's helpful in our setting is, well, let's look at how the beta looks like. So beta 2, 2 looks like this. And as I said, if this is the prior, the posterior is just adding alpha s and alpha ns to the 2 parameters. So let's look at like a higher setting, beta 3, 2, which is just adding 1 and 0, alpha s corresponding to 1, alpha ns corresponding to 0. You see that now it's starting to shift towards, it's starting to be skewed, right, towards one end. And beta 30, 20 kind of looks very, very peaked. So what happens is, as you're taking in more training data, your alpha s and alpha ns are increasing, and so your distribution is becoming more and more peaked, right? So you might start off with a fairly, smooth distribution over what you think your probability of being spam or not spam is, and then the data guides you towards one value. It starts to peak around some value. Right? So that's the sort of meaning of, if you want to think of these parameters, is that you're taking your whatever initial belief, which corresponding to these parameters, and making it more and more peaked as you collect more data. And in fact, as you get more data, the effect of the prior is washed out. If you have a lot of infinite training data, n tends to infinity, and alpha and s and alpha ns, you have a lot of examples of spam and not spam emails, you can pretty much forget about what beta was. And your distribution is going to be very, very peaked around some particular value that's completely decided by the data. Right? All right, so let me just say that now the map rule actually says that instead of maximizing just the likelihood, we are going to maximize the product of likelihood and the prior, which is just the maximizing the posterior probability. And if you do that, then the map estimate turns out to be, we are just looking for the maximum of this distribution, which is our posterior distribution. And that's just, it's again another relative count, but it now involves beta s and beta ns also. And you can think of these as, now we are doing relative counts, but we have inflated our counts by whatever the parameter beta s and beta ns was. So we have thrown in some artificial counts. It's as if we hallucinated when we assumed that our prior distribution was a beta with beta s as a parameter for spam and beta ns as a parameter for not spam. It's as if we are saying we had extra beta s examples of spam emails and beta ns examples of not spam emails. Even though we didn't have them before, we just hallucinate as if we do, and we add those counts in. And now, as you can see, even if you don't have enough training data, even if alpha s is 0, your map estimate is not going to be 0. It's going to be some well-defined number. Right?
Is there any significance of the -1 and -2 though?
That's not significant, at least as far as I know. That just comes up because of the beta distribution. Yeah. Because if you see that the beta distribution, the parameters are beta s and beta ns, but the exponents are -1. So it just comes from there. Okay. All right. So I think I'm out of time. So, but let me just summarize MLE versus map. That the maximum likelihood estimate tries to get the maximum value of your likelihood of your data under some parameter and pick the value of the parameter that maximizes the likelihood. Here you also take your prior belief into account. And for next time, you should think about when are the two the same. Okay? And we'll meet next time and finish this up.